far beyond Neptune, where sunlight fades into a cold, distant glow, there is a world almost untouched by time. A world covered in frozen methane, locked in temperatures so low that even the air would turn to ice. This is Makemake. Discovered in 2005, Makemake is one of the largest dwarf planets in the Kuiper Belt, a region filled with ancient remnants from the birth of the solar system. It orbits the Sun more than 6 billion kilometers away, in a place where darkness dominates and change happens slowly. At first, Makemake seemed simple, a small, icy world, quiet, frozen, unchanging. But the more astronomers studied it, the stranger it became. Unlike Pluto, Makemake has no thick atmosphere. Even though its surface is covered with volatile ices that should easily evaporate under sunlight, its surface is unusually bright, almost perfectly reflective, as if it has been freshly coated with ice. Yet there is no clear process explaining how. And for years it appeared to be completely alone. No rings, no major companions, nothing. Until something unexpected was discovered. A tiny, dark moon, orbiting silently around this frozen world. A clue that Makemake may not be as simple as it first appeared. In this video from Stellar Depth, we explore the distant dwarf planet Makemake, its strange surface, its hidden moon, and the mysteries that still surround one of the most isolated worlds in our solar system. The story of Makemake begins in one of the most distant and mysterious regions of our solar system, the Kuiper Belt. This vast region lies far beyond the orbit of Neptune, stretching billions of kilometers into the cold darkness of space. Unlike the inner solar system, where planets dominate the landscape, the Kuiper Belt is filled with countless icy remnants left over from the formation of the solar system more than 4.5 billion years ago. These objects are ancient. Many of them have barely changed since the earliest days of planetary formation. In a sense, the Kuiper Belt is a cosmic time capsule, a frozen archive preserving the materials that once built the planets. For centuries, astronomers had suspected that something existed beyond Neptune. The outer solar system seemed too empty, too quiet. Mathematical predictions hinted that distant objects might be lurking in the darkness. But for most of human history, these objects remained invisible. The first real confirmation came in 1992, when astronomers discovered an object called 1992 QB1, the first known Kuiper Belt object beyond Pluto and Charon. Suddenly, the outer solar system was no longer empty. It was crowded. Since that discovery, astronomers have identified thousands of Kuiper Belt objects, ranging in size from small chunks of ice to worlds hundreds or even thousands of kilometers across. Some of them rival Pluto in size. Some may even hide oceans beneath their frozen surfaces. And among these distant worlds lies Makemake. Makemake was discovered in 2005 by a team of astronomers led by Mike Brown at the Palomar Observatory in California. The same team had recently discovered another large object called Eris, which would eventually play a key role in redefining what we consider a planet. At the time, astronomers were scanning the sky systematically, searching for faint, moving objects in the outer solar system. These objects move extremely slowly against the background stars because of their enormous distance from the Sun. Detecting them requires patience, precision, and powerful telescopes. When Makemake was first detected, it appeared as nothing more than a faint, moving point of light. But even that tiny point contained valuable information. By measuring its brightness and motion, astronomers quickly realized that this object was unusually large enough to be considered a dwarf planet. Makemake is roughly 1,430 kilometers in diameter, making it one of the largest known objects in the Kuiper Belt, after Pluto and Eris. Despite its relatively small size compared to the major planets, Makemake is massive enough for its own gravity to pull it into a nearly spherical shape. That characteristic, being round due to gravity, is one of the defining features of dwarf planets. Makemake was officially classified as a dwarf planet in 2008, when the International Astronomical Union introduced the new category following the controversial reclassification of Pluto. But Makemake's discovery was significant for another reason. It revealed that the Kuiper Belt contains multiple objects large enough to resemble small planets. Before 2005, Pluto had seemed unique, a lone outpost on the edge of the solar system. But Makemake, Eris, and several others showed that Pluto was not alone. Instead, it was part of an entire population of distant icy worlds. Makemake orbits the Sun at an average distance of about 45 astronomical units, which means it is roughly 45 times farther from the Sun than Earth. At that distance, sunlight is incredibly weak. If you stood on the surface of Makemake, the Sun would appear as nothing more than an extremely bright star in the sky, far smaller than the Sun we see from Earth. Temperatures on Makemake's surface hover around minus 240 degrees Celsius. That is cold enough to freeze substances that remain gaseous on Earth. Methane, nitrogen, and other volatile compounds can solidify into ice under such conditions, and these exotic ices play a key role in shaping the surface of Makemake. Unlike rocky planets such as Earth or Mars, Makemake is believed to be composed primarily of water ice, mixed with frozen methane and possibly nitrogen. These materials give the dwarf planet its distinct appearance. One of the most surprising discoveries about Makemake is its exceptionally bright surface. In fact, Makemake reflects a large percentage of the sunlight that reaches it. Astronomers describe this property using a measurement called albedo, which represents how reflective a surface is. Makemake's albedo is estimated to be around 0.8, meaning it reflects about 80% of the sunlight that strikes it. For comparison, Earth reflects roughly 30% of incoming sunlight. This makes Makemake one of the most reflective objects in the solar system. But why is its surface so bright? The answer likely lies in the chemistry of methane ice. When methane ice is exposed to cosmic radiation and ultraviolet light over long periods, it can transform into complex organic molecules called tholins. Tholins are reddish compounds that coat many icy bodies in the outer solar system. They are responsible for the reddish color seen on Pluto and other Kuiper Belt objects. Makemake appears to have a mixture of bright methane ice and darker tholin deposits. This combination gives the dwarf planet a slightly reddish appearance when observed through telescopes. Spectroscopic observations, which analyze the wavelengths of light reflected by Makemake, have confirmed the presence of methane ice on its surface. But interestingly, Makemake appears to have very little nitrogen ice, which is abundant on Pluto. This difference suggests that Makemake may have lost much of its nitrogen over time. Nitrogen is relatively volatile, meaning it can easily escape into space if the gravitational pull of a planet or dwarf planet is not strong enough to hold it. Because Makemake is smaller than Pluto, its gravity may not be sufficient to retain a thick nitrogen atmosphere. Instead, nitrogen may have gradually escaped into space over billions of years. This process could explain why Makemake appears to have a surface dominated by methane ice rather than nitrogen. But the mystery of Makemake does not end there. For many years after its discovery, astronomers believed that Makemake was completely alone. Unlike Pluto, which has several moons, Makemake appeared to have no companions. This was unusual. Most large Kuiper Belt objects possess at least one moon. Pluto has Charon, along with 4 smaller moons. Eris has a moon called Dysnomia. Even smaller objects often have tiny satellites, but Makemake seemed solitary. Some scientists speculated that Makemake might have formed in isolation, or that any moons it once had were lost long ago. Others suggested that its moons might simply be too small or too dark to detect with existing telescopes. Detecting moons around distant objects is extremely difficult. Because the objects are so far away, even large moons appear extremely faint. If a moon reflects very little light, it can easily remain invisible against the darkness of space. For years, Makemake continued its slow orbit around the Sun without revealing any companions. But that would eventually change. In 2016, astronomers using the Hubble Space Telescope made a surprising discovery. A tiny object was detected orbiting Makemake. This small moon, temporarily designated S/2015 136472-1, was later given the name MK2. MK2 is extremely faint, about 1,300 times dimmer than Makemake itself. Its dark surface reflects very little sunlight, making it extremely difficult to detect. In fact, MK2 was only visible in Hubble images because it happened to appear in just the right position relative to Makemake. This discovery solved the long-standing mystery of Makemake's apparent isolation. But it also raised new questions. Why is MK2 so dark compared to the bright surface of Makemake? And what does its existence reveal about the formation of this distant dwarf planet? These questions would lead astronomers deeper into the frozen mysteries of the outer solar system. Because Makemake, like many worlds in the Kuiper Belt, may hold clues about how planets and moons form in the most distant regions of our cosmic neighborhood. And as scientists continue to study this frozen world, Makemake is gradually transforming from a faint point of light into a complex and fascinating object, one that may reveal new insights about the history of the solar system itself. If Makemake were simply another frozen dwarf planet drifting through the Kuiper Belt, it would still be important. But what makes Makemake truly fascinating is not just where it is, it's what it's made of. Because when astronomers began studying its surface in detail, they found something unusual, something that didn't quite match what they expected. The outer solar system is filled with icy worlds. Pluto, Eris, Triton, all of them share a similar composition. Mixtures of water ice, nitrogen ice, methane, and other frozen gases. These materials behave very differently depending on temperature and gravity. Closer to the sun, they would evaporate into gases. But in the extreme cold of the Kuiper Belt, they remain frozen, forming solid layers across planetary surfaces. At first glance, Makemake seemed similar. Spectroscopic observations revealed strong signatures of methane ice, confirming that its surface is covered in frozen hydrocarbons. But something was missing. Unlike Pluto, Makemake showed very little evidence of nitrogen ice, and that difference changes everything. Nitrogen plays a crucial role in shaping the surfaces and atmospheres of icy worlds. On Pluto, nitrogen ice forms glaciers that flow slowly across the surface. It also sublimates, turning directly from solid to gas, creating a thin atmosphere that expands and contracts as Pluto moves closer to or farther from the Sun. Makemake, however, appears to lack this dynamic behavior. Without significant nitrogen ice, it cannot sustain the same kind of atmosphere or surface activity. Instead, its surface remains far more stable, frozen, static, and that raises an important question. Why does Makemake lack nitrogen? The answer likely lies in its size and gravity. Makemake is smaller than Pluto. That means its gravitational pull is weaker. And in the outer solar system, gravity determines whether a body can hold on to volatile materials like nitrogen. Over billions of years, nitrogen molecules on Makemake may have gradually escaped into space. Each molecule, moving at just the right speed, could overcome the dwarf planet's gravity and drift away. Slowly, steadily, the nitrogen reservoir would shrink, leaving behind a surface dominated by heavier, less volatile materials like methane. Methane is more stable under these conditions. It does not escape as easily. So it remains, coating the surface in bright, reflective ice. But methane ice does not remain unchanged forever. Even in the distant Kuiper Belt, Makemake is exposed to cosmic radiation and ultraviolet light from the sun. These forms of radiation interact with methane molecules, breaking them apart and recombining them into more complex compounds. Over time, this process creates a layer of organic material known as tholins. Tholins are dark, reddish substances that form on the surfaces of many outer solar system bodies. They are responsible for the reddish hues seen on Pluto, Triton, and other icy worlds. Makemake's surface appears to contain both bright methane ice and darker tholin deposits. This combination gives the dwarf planet a slightly reddish tint, a subtle color difference that reveals the chemical processes shaping its surface. But the presence of tholins also raises another question. If radiation is constantly transforming the surface, why is Makemake still so bright? Over time, tholins should accumulate and darken the surface. Yet Makemake remains one of the most reflective objects in the solar system. This suggests that something is refreshing the surface, replacing older, darker material with new, brighter ice. But what could cause that? On Pluto, surface renewal occurs through geological activity. Nitrogen glaciers flow, ice moves, and the landscape is constantly reshaped. Makemake, however, does not appear to have that kind of active surface, so the source of its brightness remains uncertain. One possibility is that impacts play a role. Even in the distant Kuiper Belt, collisions still occur. When an impact strikes the surface of Makemake, it can expose fresh ice from beneath. This newly exposed ice would be brighter than the older, weathered surface. Over time, repeated impacts could maintain a relatively high albedo. Another possibility involves seasonal processes. Although Makemake is extremely far from the Sun, its orbit is slightly elliptical. That means it experiences small changes in temperature over the course of its long year. When Makemake is closer to the Sun, some of its surface ices may sublimate, turning into gas. When it moves farther away, those gases could refreeze onto the surface. If methane undergoes this cycle, it could create a thin, fresh layer of ice that keeps the surface bright. But without nitrogen, this process would be far less dramatic than what we see on Pluto. Still, even small seasonal changes could contribute to the renewal of the surface. And then, there's the question of an atmosphere. For years, astronomers debated whether Makemake might possess a temporary atmosphere. Not a permanent one like Earth's, but a thin envelope of gas that appears when the dwarf planet is closer to the Sun. Observations in 2011 provided an important clue. When Makemake passed in front of a distant star, an event known as a stellar occultation, astronomers expected to see a gradual dimming of the starlight if an atmosphere was present. Instead, the light disappeared almost instantly. This sharp transition suggested that Makemake does not have a significant atmosphere, at least not at the time of observation. This finding reinforced the idea that Makemake has lost most of its volatile gases. Without nitrogen, it cannot sustain the kind of atmospheric cycles seen on Pluto. Instead, it remains a cold, airless world. A frozen surface exposed directly to the vacuum of space. Yet, despite its apparent simplicity, Makemake continues to reveal unexpected complexity. Its surface composition, brightness, and lack of atmosphere all point to a history shaped by subtle processes operating over billions of years. Processes that are difficult to observe directly, processes that leave only faint clues behind. And then there is its moon. The discovery of Mk2 in 2016 added another layer to the mystery, because Mk2 is not just small, it is extremely dark. While Makemake reflects most of the sunlight that reaches it, Mk2 reflects very little. Its surface is likely covered in dark material, possibly rich in tholins or other complex organic compounds. This contrast between Makemake and its moon is striking. Two objects orbiting the same system, yet with completely different surface properties. Why is one bright and the other dark? One possibility is that Mk2 formed from material that is fundamentally different from Makemake's surface. Perhaps it originated from a collision involving a darker object, or perhaps it represents older, unprocessed material that has not been resurfaced by impacts or seasonal processes. Another possibility is that the difference is related to size. Because Mk2 is so small, it may not retain volatile ices as effectively as Makemake. Any methane or other bright ices on its surface may have escaped long ago, leaving behind darker material. Understanding this contrast could provide important clues about the history of the Makemake system, and more broadly, about how dwarf planets and their moons form in the Kuiper Belt. Because every detail, from the composition of the surface to the presence or absence of an atmosphere, tells a story. A story written in ice, in radiation, in collisions, and in the slow passage of time across billions of years. Makemake may appear quiet and frozen, but beneath that stillness lies a complex history, one that scientists are only beginning to unravel. For years, Makemake appeared to be completely alone. No rings, no visible companions, no obvious interactions with anything else in its distant orbit. In the outer solar system, that kind of isolation is unusual. Most large objects in the Kuiper Belt have at least one moon. Pluto has an entire system of satellites. Eris has dysnomia. Even smaller bodies often host tiny companions. But Makemake seemed different. It drifted through space in silence, a solitary frozen world more than 6 billion kilometers from the sun. And that raised an important question. Was Makemake truly alone, or were we simply unable to see what was there? Detecting moons in the Kuiper Belt is extremely difficult. These objects are faint to begin with, reflecting only a tiny fraction of the already weak sunlight that reaches them. A small moon orbiting a dwarf planet may be thousands of times dimmer than its parent body. If that moon has a dark surface, it becomes even harder to detect. For years, astronomers searched. They observed Makemake with powerful telescopes, including the Hubble Space Telescope, looking for any sign of a companion. But nothing appeared. Until 2016, that year, a team of astronomers analyzing Hubble images noticed something unusual, a faint point of light located very close to Makemake. At first, it was easy to dismiss. Noise, a background object, a coincidence. But when they examined additional images, the faint object appeared again, always near Makemake, always moving with it. It was not a background star. It was orbiting the dwarf planet. Makemake had a moon. The object was given a temporary designation, S/2015, 136472-1. Later, it would be referred to as MK2. Its discovery solved the mystery of Makemake's apparent isolation. But it also introduced a new puzzle. Because MK2 is unlike most moons in the outer solar system, it is extremely dark. Estimates suggest that MK2 reflects only a small fraction of the light that reaches it, perhaps as little as 4%. For comparison, Makemake reflects around 80%. That means MK2 is not just dim because it is small. It is dim because its surface absorbs most of the light that strikes it. This contrast between Makemake and its moon is striking. One bright, one dark. Two bodies orbiting together yet appearing completely different. And that difference may hold clues about how the system formed. To understand this, scientists must consider how moons form around dwarf planets. There are two primary possibilities. The first is capture. In this scenario, MK2 formed somewhere else in the Kuiper Belt and was later captured by Makemake's gravity. If this happened, MK2 could have a completely different composition from Makemake. It might have originated from a darker, more carbon-rich object. Over time, it would settle into orbit around the dwarf planet. Capture events are possible, but they require very specific conditions. For a capture to occur, energy must be lost from the system. Otherwise, the object would simply pass by and continue on its path. This can happen if a third object is involved, or if interactions with surrounding debris slow the incoming body. But in the sparse environment of the Kuiper Belt, such events are relatively rare. The second possibility is formation from a collision. In this scenario, Makemake experienced a significant impact in the past. A collision with another Kuiper Belt object could have ejected material into orbit around the dwarf planet. Some of that material would escape. but some would remain bound by gravity, eventually forming a moon. This is the same basic process believed to have formed Earth's moon. If Mk2 formed this way, its composition should be related to Makemake's interior. But here is where the mystery deepens. If Mk2 formed from material ejected from Makemake, why is it so dark? Makemake's surface is bright, covered in methane ice, but Mk2 appears to lack that reflective layer. One possibility is that Mk2 represents older, unprocessed material. When a collision occurs, it can expose deeper layers of a body, layers that may be darker and richer in complex organic compounds. If Mk2 formed from such material, it could have a composition very different from Makemake's surface. Another possibility involves size and gravity. Mk2 is extremely small. That means its gravity is weak, far weaker than Makemake's. Because of this, it may not be able to retain volatile ices like methane. Over time, any bright ices on its surface could have sublimated and escaped into space. What remains would be darker, less reflective material. In this way, Mk2 could have started out more similar to Makemake, but gradually evolved into a darker object. This process would create the stark contrast we observe today. But Mk2 is not just interesting because of its composition. Its orbit also provides valuable information. By studying how Mk2 moves around Makemake, astronomers can estimate the mass of the dwarf planet. The gravitational pull of Makemake determines the speed and shape of the moon's orbit. Using this information, scientists can calculate Makemake's density. And density reveals something important. Makemake appears to be composed of a mixture of rock and ice, with a significant portion of its interior likely made of rock. This suggests that it may have undergone some degree of internal differentiation, a process where heavier materials sink toward the center while lighter materials rise to the surface. If that is true, Makemake may not be as simple as it appears. Its interior may have once been warm enough to allow materials to move and separate. This would place it closer to objects like Pluto, which show signs of geological complexity. But unlike Pluto, Makemake does not currently show evidence of active processes on its surface. It appears quiet, frozen, yet the presence of Mk2 hints at a more dynamic past, a past shaped by collisions, gravitational interactions, and the gradual evolution of materials over billions of years. And there is another detail that makes Mk2 even more intriguing. Its orbit appears to be relatively close to Makemake. This means that tidal forces, the same forces that shape ring systems and influence moons, may play a role in the system. Over long periods of time, tidal interactions can alter the rotation of a body, change the shape of an orbit, and even affect internal heating. In larger systems, these effects can drive geological activity. In smaller systems like Makemake's, the effects are likely more subtle. But they still contribute to the long-term evolution of the system. Every orbit, every interaction, every tiny gravitational pull, all of it adds up over millions and billions of years. And together, these processes shape the world we observe today. Makemake and its moon are not just static objects. They are part of an ongoing story, a story of formation, interaction, and transformation in the cold outer reaches of the solar system. A story that began billions of years ago and continues even now as a small, dark moon circles a bright frozen world in the distant Kuiper Belt. To truly understand Makemake, we must step back and look not just at the dwarf planet itself, but at the environment in which it exists, the vast and mysterious region known as the Kuiper Belt. The Kuiper Belt is one of the largest structures in the solar system. Stretching from about 30 astronomical units beyond the Sun, just past Neptune, to more than 50 astronomical units, it forms a massive ring of icy debris encircling our star. Within this distant region lie hundreds of thousands of frozen objects, many of them remnants from the earliest days of planetary formation. These objects are sometimes described as leftover building blocks of the solar system. Billions of years ago, when the Sun and planets were forming from a rotating disk of gas and dust, material closer to the Sun gradually merged to form the familiar planets: Mercury, Venus, Earth, Mars, and the giant worlds beyond. But far from the Sun, conditions were different. The density of material was lower, collisions were slower, and the gravitational influence of the giant planets, especially Neptune, stirred the region, preventing many of these distant objects from merging into full-sized planets. Instead, they remained scattered fragments of ice and rock. The Kuiper Belt is therefore a frozen record of the solar system's earliest history. Makemake is one of the largest objects within this ancient region, but it is far from alone. Astronomers have identified several large bodies in the Kuiper Belt that qualify as dwarf planets. These include Pluto, Eris, Haumea, and Makemake itself. Each of these worlds is unique. Pluto is famous for its complex geology and thin atmosphere. Eris is slightly larger than Pluto and follows a highly elliptical orbit far beyond the Kuiper Belt. Haumea spins extremely rapidly and possesses a strange, elongated shape along with its own ring system. Makemake, meanwhile, appears simpler: a bright, icy world with a single small moon and a surface dominated by methane ice. Yet despite these differences, all of these dwarf planets share a common origin. They formed in the early solar system, when countless icy bodies orbited the young Sun. Over time, gravitational interactions, particularly with Neptune, reshaped the outer solar system dramatically. One of the most important theories explaining this process is known as the Nice model, named after the city of Nice in France, where the theory was developed. According to this model, the giant planets did not always occupy the same positions they hold today. Early in the solar system's history, Jupiter, Saturn, Uranus, and Neptune migrated through the protoplanetary disk, shifting their orbits as they interacted with surrounding material. During this migration, Neptune moved outward into the region that is now the Kuiper Belt. As it did so, its powerful gravity scattered countless icy bodies into new orbits. Some were pushed outward into the distant Kuiper Belt. Others were thrown inward toward the Sun, and many were ejected from the solar system entirely. This chaotic reshaping of the outer solar system created the structure we observe today. The Kuiper Belt became a reservoir of ancient objects, while other scattered objects were pushed into highly elliptical orbits far beyond it. Makemake is believed to have formed during this turbulent period. Originally, it may have formed closer to the Sun than its current orbit suggests, but gravitational interactions with Neptune likely pushed it outward into the distant region where it now resides. Today, Makemake follows a relatively stable orbit around the Sun, completing one full revolution approximately every 305 Earth years. That means that since its discovery in 2005, Makemake has moved only a tiny fraction of the way along its long journey around the Sun. But even though its orbit is stable today, the early history of Makemake may have been far more chaotic. In the crowded environment of the early Kuiper Belt, collisions were more common. Large objects occasionally struck one another, shattering surfaces and sending debris into space. Some of these collisions may have created moons. Others may have reshaped the surfaces of dwarf planets. It is possible that Makemake itself experienced such a collision. If MK2, its small moon, formed from debris created during an impact, then Makemake's past may include a dramatic event that blasted material into orbit around the dwarf planet. But Makemake's location in the Kuiper Belt also raises another important question. Why did it grow large enough to become a dwarf planet, while most Kuiper Belt objects remained small? The answer likely involves local concentrations of material during the early stages of solar system formation. In certain regions, slightly denser clusters of ice and rock allowed objects to grow larger through repeated collisions and mergers. Over millions of years, these bodies gradually accumulated mass. Eventually, some became large enough for their own gravity to pull them into spherical shapes. Makemake is one of those survivors. But even among the largest Kuiper Belt objects, Makemake stands out for its remarkably bright surface. Most objects in the Kuiper Belt are dark. Over billions of years, radiation from cosmic rays and ultraviolet light gradually alters surface materials, creating darker organic compounds. These compounds accumulate over time, giving many Kuiper Belt objects a reddish or brownish appearance. Makemake, however, appears unusually bright. Its methane-rich surface reflects a large percentage of the sunlight that reaches it. This brightness suggests that Makemake's surface may have been resurfaced relatively recently on geological timescales. Fresh ice exposed by impacts could maintain the high reflectivity observed today. Alternatively, slow cycles of sublimation and redeposition may refresh parts of the surface. But because Makemake lacks a thick atmosphere, these processes are not fully understood. In many ways, Makemake represents an intermediate case between larger dwarf planets like Pluto and smaller Kuiper Belt objects. It is large enough to maintain a spherical shape, large enough to host a moon, yet small enough that it cannot retain a significant atmosphere. This balance makes it an important object for scientists studying the outer solar system. By comparing Makemake with other dwarf planets, astronomers can better understand how size, gravity, and composition influence the evolution of icy worlds. And beyond the scientific details, Makemake also represents something deeper. A reminder of how vast and unexplored the outer solar system truly is. Even today, our knowledge of the Kuiper Belt remains incomplete. Many large objects likely remain undiscovered. Some may be nearly as large as Pluto. Others may possess moons, rings, or unexpected geological features. Every new discovery reveals that the distant edges of our solar system are far more complex than once imagined. Makemake is part of that story. A frozen world drifting slowly through an ancient region filled with the remnants of planetary formation. A world whose surface preserves clues about processes that occurred billions of years ago. And as astronomers continue to study Makemake and other Kuiper Belt objects, they are gradually uncovering the history of a region that remained hidden from humanity for most of our existence. A region where time moves slowly, and the secrets of the early solar system remain locked in ice. When astronomers look at Makemake through powerful telescopes, they see only a distant point of light. Even the most advanced observatories cannot capture detailed images of its surface. At more than 6 billion kilometers from the Sun, Makemake is simply too far away. And yet, despite this distance, scientists have managed to learn an astonishing amount about this frozen world, not through photographs, but through light. Every object in space reflects sunlight in a slightly different way. By carefully studying the wavelengths of light reflected from Makemake's surface, astronomers can determine the chemical substances present there. This technique is known as spectroscopy, and it has become one of the most powerful tools in planetary science. When sunlight strikes the surface of Makemake, some wavelengths are absorbed while others are reflected. Each type of ice or mineral leaves a unique signature in the reflected light, almost like a fingerprint. By analyzing these fingerprints, scientists can identify the materials covering the dwarf planet's surface. And what they discovered was remarkable. Makemake's surface appears to be dominated by methane ice. Methane, the same compound that exists as a gas on Earth, becomes a solid under the extremely low temperatures found in the Kuiper Belt. At roughly -240 degrees Celsius, methane freezes into crystalline ice that can blanket an entire planetary surface. This methane ice is one of the main reasons Makemake appears so bright. Methane ice reflects sunlight very efficiently, giving the dwarf planet a high albedo, or reflectivity. In fact, Makemake reflects around 80% of the sunlight that reaches it. For comparison, Earth reflects about 30%. This makes Makemake one of the most reflective large objects in the solar system. But methane ice alone does not explain everything astronomers observe. When scientists analyzed Makemake's spectrum in greater detail, they noticed subtle variations in the reflected light. These variations suggested that the methane ice is not perfectly pure. Instead, it has been chemically altered by cosmic radiation. Even at the edge of the solar system, objects are constantly bombarded by high-energy particles from space. Over millions and billions of years, these particles interact with surface materials and gradually change their chemical structure. When methane ice is exposed to radiation, it can transform into complex organic molecules known as tholins. Tholins are dark, reddish substances that form through chemical reactions involving methane, nitrogen, and ultraviolet light. These compounds are believed to be common throughout the outer solar system. They are responsible for the reddish coloration of many Kuiper Belt objects, including Pluto. Makemake's surface appears to contain a mixture of bright methane ice and darker tholin deposits. This combination produces the faint reddish tint observed in telescopic images. But the presence of tholins creates another puzzle. If radiation is constantly producing dark compounds on the surface, why does Makemake remain so bright? Over time, tholins should accumulate and gradually darken the dwarf planet. Yet Makemake continues to reflect large amounts of sunlight. This suggests that something is renewing the surface, exposing fresh methane ice faster than radiation can darken it. One possible explanation involves impacts. Although the Kuiper Belt is sparse compared to regions closer to the Sun, collisions still occur. When small icy objects strike Makemake's surface, they can blast away older layers of material and reveal fresh ice underneath. These newly exposed surfaces would be much brighter than the surrounding terrain. Even relatively small impacts could create patches of bright ice that maintain the dwarf planet's high reflectivity. Another possibility involves slow seasonal cycles. Makemake's orbit around the Sun is not perfectly circular. At certain points in its orbit, the dwarf planet is slightly closer to the Sun, receiving marginally more sunlight. Although the difference is small, it may still be enough to cause some methane ice to sublimate, turning directly from solid into gas. When Makemake moves farther from the Sun again, that gas could refreeze onto the surface, creating a thin layer of fresh ice. If this process occurs, it would act like a natural resurfacing mechanism. Over long periods of time, these cycles could help maintain Makemake's bright appearance. But without a significant atmosphere, the scale of these processes would likely be limited. Unlike Pluto, which has a thin nitrogen atmosphere that moves material across its surface, Makemake's environment is far more static. Still, even subtle changes could play a role in maintaining its reflective surface. Another fascinating aspect of Makemake's composition involves water ice. Although methane dominates the surface spectrum, observations suggest that water ice may exist beneath the outer layers. Water ice behaves very differently from methane. It is far less volatile and much more stable under Kuiper Belt conditions. In fact, water ice forms the structural backbone of many icy bodies in the outer solar system. If Makemake contains a significant amount of water ice beneath its surface, it could influence the dwarf planet's internal structure. Over billions of years, radioactive elements inside Makemake may have generated small amounts of heat. This heat could have caused internal materials to shift and separate, a process known as differentiation. In differentiated bodies, denser materials sink toward the center, while lighter materials rise toward the surface. If Makemake experienced this process, it might possess a rocky core surrounded by layers of ice. But because Makemake is relatively small compared to major planets, any internal heating would have been limited. Today, the dwarf planet is likely geologically inactive. Its surface probably changes very slowly, shaped primarily by impacts and radiation rather than internal forces. Yet even without active geology, Makemake remains scientifically valuable, because its surface preserves clues about chemical processes occurring in the outer solar system. The formation of tholins, for example, may be linked to the chemistry that produces complex organic molecules in space. Some scientists even speculate that similar processes may have contributed to the early chemistry that eventually led to life on Earth. In this way, studying distant icy worlds like Makemake can provide insights far beyond their own surfaces. They help scientists understand how organic chemistry evolves in extreme environments. They reveal how radiation alters materials over long periods of time. And they show how planetary surfaces can preserve ancient chemical records. Makemake may appear quiet and frozen, but its surface is constantly interacting with the environment of deep space. Cosmic rays strike it. Ultraviolet light alters its chemistry. Micrometeorites pepper its surface with tiny impacts. All of these processes leave their mark. Slowly, silently, the dwarf planet evolves, and through careful observation, astronomers continue to uncover the secrets hidden within the faint light reflected from this distant frozen world. Far from the warmth of the inner solar system, Makemake exists in an environment that is both quiet and unforgiving. Temperatures remain extremely low, sunlight is weak, and the surrounding region of space is sparsely populated. Yet, despite this stillness, the dwarf planet continues to interact constantly with the forces of the outer solar system. To understand Makemake more deeply, scientists must look not only at its surface composition or its small moon, but also at the environmental conditions shaping the dwarf planet over billions of years. In the Kuiper Belt, distance changes everything. At Earth's distance from the Sun, sunlight is strong enough to warm surfaces, drive atmospheric circulation, and power dynamic weather systems. But at Makemake's distance, more than 45 astronomical units from the Sun, sunlight is dramatically weaker. The Sun appears almost 1,000 times dimmer than it does from Earth. Instead of a blazing disk dominating the sky, the Sun would appear as an extremely bright star, casting only faint illumination across the frozen landscape. This weak sunlight plays a crucial role in determining what materials can exist on Makemake's surface. Substances that are gases on Earth, methane, nitrogen, carbon monoxide, can freeze solid under these conditions. The dwarf planet therefore behaves almost like a giant freezer, preserving volatile materials that would evaporate much closer to the Sun. But even in such cold conditions, these materials are not completely stable. Over long periods of time, molecules on the surface gain enough energy to escape into space. This process, known as thermal escape, occurs when individual molecules move fast enough to overcome the gravitational pull of the body they are on. Because Makemake's gravity is relatively weak compared to larger planets, lighter molecules are especially vulnerable to escaping. This is why scientists believe Makemake has lost much of its original nitrogen over time. Billions of years ago, the dwarf planet may have possessed a surface composition more similar to Pluto's, with large quantities of nitrogen ice. But as nitrogen molecules slowly escaped into space, the remaining surface became dominated by heavier materials like methane. This gradual loss of volatile materials is a key part of Makemake's evolution, and it illustrates a broader principle in planetary science. Size determines destiny. Large bodies like Earth or Jupiter have enough gravity to retain thick atmospheres for billions of years. Smaller bodies like Makemake cannot hold on to gases as effectively. Over time, their surfaces become chemically altered as lighter materials disappear. But gravity is not the only force acting on Makemake. The dwarf planet also experiences the effects of cosmic radiation. Beyond the protective influence of the Sun's stronger magnetic environment, objects in the Kuiper Belt are exposed to a constant stream of high-energy particles originating from distant supernovae and other energetic events across the galaxy. These cosmic rays strike the surface of Makemake continuously. When they interact with surface materials, they break chemical bonds and trigger new reactions between molecules. Methane molecules may be split apart, allowing carbon atoms to recombine into more complex organic compounds. Over time, these reactions produce dark reddish materials, the tholins that coat many outer solar system bodies. This radiation-driven chemistry slowly transforms the surface layer of Makemake. But unlike geological processes, which can reshape landscapes rapidly on planetary timescales, radiation chemistry operates extremely slowly. The accumulation of tholins may take millions or even billions of years. And yet, given enough time, these changes become significant. They gradually darken surfaces, alter spectral signatures, and provide clues about the chemical history of distant worlds. Another environmental factor shaping Makemake is the constant impact of micrometeorites. Even in the distant Kuiper Belt, tiny fragments of rock and ice travel through space at high speeds. When these particles strike Makemake's surface, they release small bursts of energy that can alter surface materials. Most of these impacts are extremely small. They do not create large craters or dramatic surface features. Instead, they act like a slow form of cosmic sandblasting. Over time, billions of tiny impacts gradually erode the surface layer. They mix surface materials, expose deeper ice, and redistribute particles across the dwarf planet's landscape. This process is known as space weathering, and it affects virtually every airless body in the solar system. On Makemake, space weathering likely plays an important role in maintaining the balance between bright ice and darker tholin deposits. Impacts may occasionally expose fresh methane ice from beneath the surface, temporarily brightening certain regions. At the same time, radiation slowly darkens those areas again. The result is a dynamic equilibrium between bright and dark materials. Even though Makemake appears frozen and unchanging, its surface is constantly evolving through these subtle interactions. And then, there is the influence of the sun itself. Although sunlight is extremely weak at Makemake's distance, it still affects the dwarf planet in important ways. Makemake's orbit around the Sun takes approximately 305 Earth years. During this long journey, the dwarf planet moves slightly closer to and farther from the Sun. These changes in distance cause small variations in temperature. Even a slight increase in temperature can trigger the sublimation of methane ice. When methane sublimates, it transforms directly from solid into gas without passing through a liquid phase. This gas may briefly form a thin, localized atmosphere around Makemake before escaping into space. If conditions later cool again, some of the methane could refreeze onto the surface, creating new layers of ice. Although scientists have not directly observed a stable atmosphere on Makemake, these seasonal processes may still occur on small scales. If they do, they could help explain why Makemake's surface appears unusually bright compared to many other Kuiper Belt objects. But perhaps the most fascinating aspect of Makemake's environment is how isolated it truly is. At a distance of more than 6 billion kilometers from the Sun, Makemake exists in a region where change happens incredibly slowly. Orbital periods last centuries. Surface chemistry evolves over millions of years. Impacts that would dramatically reshape a smaller asteroid may leave only subtle traces on a body as large as Makemake. In this way, Makemake represents a kind of cosmic archive. Its surface preserves records of processes that have unfolded across vast spans of time. By studying these distant icy worlds, scientists can learn about the early solar system, a time when countless icy bodies were forming, colliding, and migrating under the influence of gravity. Makemake may not display dramatic geological features like volcanoes or moving glaciers, but its frozen surface still contains valuable information about how planets and dwarf planets evolve in the coldest regions of space. And as astronomers continue to refine their observations, new clues may emerge. Clues hidden in faint spectral signatures, clues revealed by subtle variations in brightness, clues that help scientists piece together the story of a world that has remained in deep freeze since the earliest days of our solar system. Makemake may be distant, quiet, and frozen, but in the language of planetary science, it still has much to say. There is something unusual about worlds like Makemake, not just because of their distance, not just because of their cold, but because of what they represent. They are not fully planets, and yet they're not small enough to be ignored. They exist in a kind of boundary, a category that did not even exist until recently, the category of dwarf planets. And to understand Makemake, you have to understand why that category exists at all. For most of modern history, the solar system seemed simple. There were 9 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Pluto was discovered in 1930, and for decades it was considered the 9th planet. But as telescopes improved and observations became more precise, astronomers began to notice something. Pluto was not alone. Objects similar in size and composition began to appear in the outer solar system. At first, they were small, but then came discoveries that changed everything. In the early 2000s, astronomers discovered several large objects in the Kuiper Belt. One of them was Eris, a dwarf planet slightly more massive than Pluto. Another was Haumea, with its strange, elongated shape and rapid rotation. And then there was Makemake. These discoveries raised a problem. If Pluto is a planet, then what are these new objects? Are they planets too? If so, the number of planets in the solar system could grow rapidly. There might be dozens, maybe even hundreds. But if they are not planets, then what distinguishes Pluto from them? The question became unavoidable. And in 2006, the International Astronomical Union made a controversial decision. They redefined what it means to be a planet. According to the new definition, a planet must meet 3 criteria. It must orbit the Sun. It must be massive enough for gravity to shape it into a spherical form. And it must have cleared its orbit, meaning it dominates its orbital region and is not surrounded by other objects of similar size. Pluto failed this 3rd requirement, and so did Makemake. Both objects orbit within the Kuiper Belt, a region filled with many similar bodies. They do not dominate their surroundings. Instead, they share their orbital space with countless other objects. Because of this, they were placed into a new category, dwarf planets. This decision was controversial. Many people felt that Pluto had been demoted. But from a scientific perspective, the new classification helped clarify something important. The solar system is not divided simply into planets and everything else. There are intermediate worlds, objects like Makemake that are large enough to be spherical, complex enough to be interesting, but not dominant enough to be considered full planets. And Makemake is one of the most important examples of this category because it sits right at the boundary. Large, but not dominant. Complex, but not fully understood. A world that challenges simple definitions. But beyond classification, there is a deeper question. What does it mean to be a planet? Is it just about size, gravity, orbital dominance, or is it something more fundamental? Makemake forces us to think about these questions, because in many ways it behaves like a planet. It has a defined shape. It has a surface composed of different materials. It has a moon. It has a history shaped by collisions and chemical processes. And yet, it is not considered a planet. This ambiguity reflects a larger truth about the universe. Nature does not always fit neatly into categories. We create definitions to organize our understanding, but those definitions are often imperfect. They are tools, not absolute truths, and objects like Makemake exist in the spaces between those definitions. They remind us that the universe is more complex than our classifications. But Makemake's significance goes beyond its status as a dwarf planet. It is also part of a larger population of objects that may hold clues about the formation of planetary systems. Because the Kuiper Belt is not unique, similar structures exist around other stars. Astronomers have observed debris disks surrounding distant stars, rings of dust and ice, that resemble the early stages of planetary formation. These disks may contain objects similar to Makemake. Studying Makemake therefore helps scientists understand not only our own solar system, but also how planetary systems form elsewhere in the galaxy. It provides a local example of processes that may be occurring around countless other stars. And then there is another perspective, a more human one. When we look at Makemake, we are looking at something incredibly distant, something that takes over 300 years to complete a single orbit around the Sun, something that has remained largely unchanged for billions of years. In a sense, Makemake exists on a completely different timescale from our own. Human history spans thousands of years. Makemake's history spans billions. Its changes are slow, subtle, almost imperceptible within a human lifetime. And yet, those slow processes tell a story of formation, of transformation, of survival in one of the coldest regions of the solar system. It is easy to think of distant objects as static, as unchanging. But that is an illusion. Makemake is constantly evolving. Its surface is altered by radiation. Its materials shift over time. Its moon orbits, influenced by gravity. Even in the quietest regions of space, change is always happening, just on timescales far longer than we are used to. And this is what makes Makemake so important, not because it is dramatic, not because it is active in the way Earth or Mars is, but because it preserves a record of processes that have been unfolding for billions of years. Processes that shaped the early solar system, processes that continue to shape distant worlds today. Makemake is not just a frozen object in space. It is a piece of a much larger puzzle, a puzzle that spans the entire solar system and beyond. And by studying it, scientists are not just learning about one distant world. They are learning about the boundaries between categories, the limits of our definitions, and the deeper complexity of the universe itself, a complexity that cannot always be reduced to simple labels, a complexity that continues to reveal itself, one distant world at a time. There is something almost paradoxical about Makemake. It is one of the most distant worlds in the solar system, yet it is also one of the most revealing. Because despite its silence, despite its frozen surface and lack of atmosphere, Makemake carries within it clues about processes that shaped not just the outer solar system, but the entire planetary system we live in. To understand why, we have to look at Makemake not as an isolated object, but as part of a much larger structure. A structure that extends far beyond Neptune. A structure that represents one of the earliest stages of planetary formation, the Kuiper Belt. This region is not just a collection of random icy bodies. It is the remnant of the protoplanetary disk, the vast cloud of gas and dust that surrounded the young sun billions of years ago. Closer to the sun, that material eventually formed the planets. But farther out, where the density was lower and temperatures were colder, the process of planet formation was incomplete. Instead of forming a few large bodies, the material remained fragmented. Objects like Makemake are the result of that incomplete process. They are protoplanets that never became full planets, and that makes them incredibly valuable, because they preserve a snapshot of what the early solar system looked like. Makemake is, in a sense, a fossil. Not a fossil of life, but a fossil of planetary formation. Its composition tells us what materials were present in the outer solar system billions of years ago. Its structure reveals how those materials were distributed. And its current state reflects the long-term evolution of those materials under extreme conditions. But Makemake is not alone in this role. Other dwarf planets, Pluto, Eris, Haumea, also preserve similar records. Each one offers a different perspective on the same underlying processes. Pluto shows us what happens when a dwarf planet retains enough volatile materials to sustain an atmosphere and active surface processes. Eris shows us what happens at even greater distances, where temperatures are lower and volatile retention becomes more stable. Haumea shows us the effects of rapid rotation and catastrophic collisions. And Makemake shows us what happens when a world sits right at the boundary, too small to retain a thick atmosphere, large enough to develop a complex surface, cold enough to preserve methane ice, but dynamic enough to show signs of change. It is a transitional object, a world that exists between categories. And because of that, it helps scientists understand how small differences in size, composition, and environment can lead to very different outcomes. For example, consider the role of gravity. Gravity determines whether a body can hold on to volatile materials. It influences the formation of moons. It shapes the internal structure of a world. Makemake's gravity is strong enough to maintain a spherical shape, but not strong enough to retain nitrogen over billions of years. That single difference, the ability to hold on to nitrogen, separates Makemake from Pluto in a fundamental way. It explains why Pluto has an atmosphere and active surface processes, while Makemake remains largely static. This highlights an important principle in planetary science. Small changes in initial conditions can produce dramatically different results. A slightly larger mass, a slightly different composition, a slightly different orbit. Over billions of years, those differences accumulate, and they shape the evolution of a world. Makemake provides a clear example of this principle. It is similar to Pluto in many ways, but the differences are just large enough to create a completely different outcome. And then, there is the question of time. Makemake's orbital period is more than 300 Earth years. That means its seasons, if they exist, last for decades or even centuries. Any changes on its surface occur extremely slowly. Processes that might take days or years on Earth could take thousands or millions of years on Makemake. This slow pace makes the dwarf planet difficult to study, but it also makes it valuable because it preserves long-term records of chemical and physical processes. On Earth, weather and geological activity constantly reshape the surface. Old features are erased, new ones appear. But on Makemake, change happens slowly, very slowly, and that means ancient features can persist. The surface becomes a record of the past, a record that scientists can read through careful observation. And then there's the broader implication. Makemake is not just important for understanding our own solar system. It also provides insight into planetary systems around other stars. Many stars are surrounded by disks of dust and debris. These disks are thought to be similar to the early solar system. Within them, planets may be forming, or may have formed already. By studying Makemake and other Kuiper Belt objects, scientists can better understand how these processes work. They can develop models that apply not just to our solar system, but to planetary systems throughout the galaxy. In this way, Makemake becomes more than just a distant object. It becomes a reference point, a local example of processes that may be universal. But perhaps the most interesting aspect of Makemake is not what we know, but what we do not know. Because despite all the observations, all the data, all the analysis, many questions remain. Does Makemake ever develop a temporary atmosphere? How does its surface evolve over time? What is the exact composition of its interior? How did its moon form? And are there other objects like it waiting to be discovered? These questions are not just about Makemake. They are about the limits of our knowledge. They remind us that even in our own solar system, a place we have studied for centuries, there are still mysteries, still unknowns, still discoveries waiting to be made. Makemake is one of those mysteries, a frozen world drifting through the darkness, quiet, distant, yet filled with clues about the origins of planets, the evolution of materials, and the structure of the solar system. And as scientists continue to study it, they are not just learning about one dwarf planet. They are learning about the processes that shape entire planetary systems, processes that began billions of years ago and continue even now in the cold and distant reaches beyond Neptune. When we think about exploring the solar system, our minds often turn to familiar places. Mars, with its dusty red deserts. Jupiter, with its massive storms. Saturn, with its spectacular rings. These worlds have been visited by spacecraft, photographed in incredible detail and studied for decades. But far beyond the orbit of Neptune lies a region that remains almost completely unexplored. A region where worlds like Makemake drift through deep darkness. A region where no spacecraft has yet traveled, except for one brief visit. The Kuiper Belt is one of the last great frontiers of the solar system. It stretches across billions of kilometers, filled with icy bodies that have remained largely unchanged since the birth of the Sun. And yet, despite its enormous size, we have only glimpsed a tiny fraction of it. Most of what we know about Kuiper Belt objects comes from telescopes observing faint points of light from Earth. But telescopes can only tell us so much. They can measure brightness. They can detect chemical signatures. They can track orbital motion. What they cannot easily reveal are the detailed landscapes of these distant worlds. For that, we need spacecraft. And so far, only one mission has ventured into this distant region: NASA's New Horizons spacecraft. Launched in 2006, New Horizons traveled for nearly a decade before reaching Pluto in 2015. When it arrived, the images it sent back stunned scientists. Pluto, once thought to be a simple frozen ball of ice, turned out to be a complex world. It had mountains of water ice towering kilometers above the surface, glaciers of nitrogen ice flowing across vast plains, and evidence of geological activity that may still be occurring today. The encounter with Pluto transformed our understanding of dwarf planets, but New Horizons did not stop there. After leaving Pluto, the spacecraft continued deeper into the Kuiper Belt. In 2019, it flew past another distant object known as Arrokoth. Arrokoth turned out to be a contact binary, two icy bodies that had gently merged together billions of years ago. Its surface appeared remarkably smooth and ancient, providing a direct glimpse into the earliest stages of planetary formation. These discoveries demonstrated something important. The Kuiper Belt is not a uniform collection of icy rocks. Each object is unique. Each one has its own history, its own composition, its own story, and that raises an exciting possibility. If a spacecraft were sent to Makemake, what might we find? The answer could completely transform our understanding of this distant world. From Earth, Makemake appears as a bright, icy sphere with a faint reddish tint. But telescopes cannot reveal its detailed surface features. Does Makemake have large impact basins like Pluto? Are there mountains of water ice rising above methane-covered plains? Are there regions where fresh ice has recently been exposed? Or perhaps darker areas where radiation has transformed the surface over billions of years? Without direct observation, these questions remain unanswered. A spacecraft mission could also reveal the true nature of Makemake's moon. MK2 is extremely dark and difficult to observe from Earth. A close flyby could determine its exact size, shape, and composition. It could reveal whether MK2 formed from a collision or was captured from elsewhere in the Kuiper Belt. And it could show how the gravitational interaction between Makemake and its moon has shaped both bodies over time. Perhaps even more intriguing is the possibility that Makemake's surface contains features we have not yet imagined. Before New Horizons reached Pluto, few scientists expected to see active glaciers, towering mountains, or such dramatic geological diversity. And yet, that is exactly what they found. Makemake could hold similar surprises. Its surface chemistry, dominated by methane ice, may produce landscapes very different from those seen on Pluto. Perhaps there are frozen methane dunes sculpted by sublimation. Perhaps the surface contains unusual crystal formations created by slow chemical processes. Or perhaps the dwarf planet hides structures beneath its icy crust that hint at past internal activity. All of these possibilities remain open, but sending a spacecraft to Makemake would not be easy. The dwarf planet lies more than 6 billion kilometers from Earth. A mission would take many years, possibly decades, to reach its destination. Even New Horizons, traveling at extraordinary speed, required 9 years to reach Pluto. Reaching Makemake could take even longer. And yet, such missions are not impossible. Advances in propulsion technology, navigation systems, and long-duration spacecraft design are making deep space exploration increasingly feasible. Future missions may one day travel through the Kuiper Belt, visiting multiple dwarf planets along the way. Makemake could be one of their targets. If that happens, the images returned could revolutionize our understanding of this distant world. For the first time, we would see its surface directly. We would observe its moon in detail. We would measure its composition with instruments far more precise than anything possible from Earth. And, perhaps most importantly, we would place Makemake into context within the broader history of the solar system. Because every world in the Kuiper Belt represents a piece of that history. Each one preserves clues about the conditions that existed billions of years ago. By studying them, scientists can reconstruct the processes that shaped our planetary system, processes that eventually led to the formation of Earth and to the emergence of life itself. Makemake may seem distant and insignificant compared to the giant planets, but in reality, it is part of the same story. A story that began in a swirling disk of gas and dust around a young star. A story that continues today, written across billions of kilometers of space, and somewhere in that vast darkness, a frozen dwarf planet continues its slow orbit around the sun. Silent, ancient, waiting for the day when humanity finally comes close enough to see it clearly. Far beyond the familiar planets, beyond the orbit of Neptune where sunlight fades into a cold and distant glow, Makemake continues its silent journey around the sun. For more than 4.5 billion years, this frozen world has traveled through the outer solar system, preserving within its icy surface a record of the earliest days of planetary formation. Unlike the inner planets, where geological activity, weather, and tectonic forces constantly reshape the landscape, Makemake has remained largely untouched by dramatic change. It exists in a region where time moves slowly, where temperatures remain locked in extreme cold, where the processes shaping a world unfold across millions and billions of years. And yet, despite this apparent stillness, Makemake has become one of the most important objects for understanding the distant reaches of our solar system. Because Makemake represents something fundamental. It is a survivor, a remnant of the early solar system that managed to grow large enough to become a dwarf planet, but not large enough to dominate its surroundings. In this sense, Makemake occupies a fascinating middle ground. It is not a major planet like Neptune. It is not a small, irregular fragment like most Kuiper Belt objects. Instead, it sits somewhere in between, a world large enough to develop complex surface chemistry, but small enough to reveal the limitations imposed by gravity and distance from the sun. This balance makes Makemake a natural laboratory for studying how icy worlds evolve. Its surface composition, dominated by methane ice and organic compounds, tells a story of chemical transformation driven by radiation and time. Its high reflectivity suggests that fresh ice is still being exposed, perhaps by impacts or slow seasonal processes. Its small moon hints at a past collision or gravitational interaction that reshaped the system long ago. And its lack of a significant atmosphere reveals how easily volatile gases can escape from smaller worlds in the outer solar system. Taken together, these features create a portrait of a world that is both simple and complex at the same time. Simple, because it lacks the dramatic geological activity seen on larger bodies like Pluto. Complex because the processes shaping its surface are subtle, gradual, and difficult to observe directly. Makemake, therefore, reminds us that planetary science is not always about spectacular phenomena. Sometimes the most important discoveries come from understanding slow processes operating over immense periods of time, processes that quietly shape the surfaces of distant worlds, processes that leave behind clues written in ice and chemistry. But Makemake's importance extends beyond its own frozen landscape, because it is part of a much larger structure, the Kuiper Belt. This distant region contains thousands, perhaps millions of icy bodies orbiting the Sun. Many of them are small, but some, like Makemake, are large enough to reveal complex histories. Each one represents a fragment of the early solar system, a preserved record of the materials and conditions that existed when the planets were first forming. By studying Makemake and its neighbors, scientists are gradually reconstructing the story of how our planetary system came into existence. They are learning how material was distributed in the early solar system, how the giant planets migrated through the protoplanetary disk, how collisions and gravitational interactions shaped the architecture of the outer solar system, and how small differences in size and composition produced dramatically different outcomes. Makemake is one piece of that puzzle, a piece that helps explain why some dwarf planets developed atmospheres while others did not, why some retain volatile materials while others lose them, why some host multiple moons while others appear almost completely isolated. In the coming decades, new telescopes will continue to refine our understanding of Makemake. Observatories such as the James Webb Space Telescope will analyze its surface composition with unprecedented sensitivity. Future ground-based telescopes, including the extremely large telescope currently under construction, will be able to observe Kuiper Belt objects in greater detail than ever before. These instruments may reveal subtle variations across Makemake's surface. They may detect changes in brightness that hint at seasonal processes. They may even discover additional companions orbiting the dwarf planet. And beyond telescopes, the possibility remains that one day a spacecraft will travel to Makemake. Just as New Horizons transformed our understanding of Pluto, a mission to Makemake could reveal landscapes we have never imagined. Perhaps towering ridges of water ice rise above plains of methane frost. Perhaps ancient impact basins dominate the surface. Or perhaps Makemake is exactly what it appears to be from afar, a quiet, frozen world preserving the memory of the early solar system. Whatever the answer, exploring Makemake would expand our understanding of planetary science in ways that cannot yet be predicted. But even without such a mission, Makemake already teaches us something important. It reminds us that the solar system is far larger and more diverse than we once believed. For centuries, humanity knew only the planets visible to the naked eye. Then, telescopes revealed Uranus and Neptune. Later discoveries uncovered Pluto and the Kuiper Belt. And with each new discovery, the boundaries of the solar system expanded. Makemake is part of that expansion, a world that was completely unknown to humanity until the early 21st century, a world that has existed for billions of years, orbiting quietly in the darkness, waiting to be discovered. Its story is a reminder that exploration is never finished. There are still distant regions of our own solar system that remain mysterious, still worlds waiting to be studied, still questions waiting to be answered. Makemake may be small compared to the giant planets, but it plays a crucial role in revealing the hidden structure of the outer solar system. And as it continues its slow orbit around the Sun, a journey that takes more than 3 centuries to complete, it remains one of the most intriguing members of the distant Kuiper Belt, a frozen mystery planet, a survivor from the birth of the solar system, and a reminder that even in the coldest, darkest corners of our cosmic neighborhood, there are still worlds full of secrets waiting to be uncovered.